Hello and welcome to IronBeetle, a show where once in a while we start with a blank screen. Okay, so let me just quickly try to fix this up. Okay, I want this to actually work. No, that's not right. Okay, yeah, this is better. Okay, let's try it again. Welcome to IronBeetle, a show where we try to do things. On the one hand, we try to understand how IronBeetle works, this pretty exciting database for financial accounting. But on the other hand, we try to understand how to build complex systems from scratch. And the latter part is by far the more interesting because, okay, maybe we'll use IronBeetle, maybe you won't use IronBeetle, but you are definitely going to interact with and design and implement your own complex systems. And in my software engineering journey, I kind of realized that, if you look at software engineering from the outside, it feels like there is layers and layers of complexity, and that you need to spend decades to understand all of that. But actually, if you start digging, you realize that hey, there are relatively few fundamental ideas, and by getting the fundamentals, you could actually gain the ability to understand everything else. So that's what we are doing. On IronBeetle, we are learning fundamentals of building a database. And I know that I promised you a Pragmatics of Consensus lecture with Toby, and then I kind of postponed it, and I will postpone it again. So it will happen. I will not repeat the mistake, and I will not say when exactly will it happen, but it will happen soon enough. And today, instead of doing smart things like consensus or what we did last time, payment and posted transfers, I want to look at a really simple and silly topic, and that is parse command line argument. It's still kind of fun thing to do. Okay, so hopefully I will be able to share a couple of useful things. Let's get back to our Hunters in the Snow. Let's get back to our IronBeetle code base. Okay. Yeah, so flags and snap tests. And the dark mode, of course. I kind of continue to prefer light mode as well for our excellent audience. I'm willing to compromise on my preferences. So, yeah, okay, let's maybe start with a little demonstration, what command line syntax we have here. So yeah, we have multiple subcommands. I think there is a help version which tells you how to pass arguments. So we can say IronBeetle format, and then we pass class to replica, blah 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 blah. So what is okay? People on the stream complain that I'm not visible. That's not really great because it actually works. Okay, let me quickly check if I can see myself. So people who have streaming problems. We had persistent problems on Twitch. And that's why we actually stream to 3 platforms, to Twitch, to YouTube, to X. And if one platform does not work for you, then you might want to check another platform. At the same time, if nothing works for you, and that's why then it probably is the case that the problem is on my side. But I've just opened YouTube, and it definitely works on YouTube right now. So okay, but thanks for checking. Like, the technical problems can appear. Okay, so parsing command line arguments. The first thing you notice here is that, like, there is like a certain syntax, and you might realize that different tools use different syntax. Like, for example, if you use, can I make this bigger? If you use like standard command line tools, there is like syntax for short options, and if you use something like Go, it has like this convention where, like, it has long options but only a single dash, and all that stuff. So you might wonder, like, what is, like, if I'm designing like command line tool, what is the actual syntax for options? Like, is there like some kind of like technical specification or whatnot? And I'm not an expert in this domain, but my general take is that it is a hot mess. Like, really, everyone is using different conventions, and there isn't like, super specified, like, hey, this is what you should do. And to kind of like pin this down very specifically, like at the root of our command line, and in general at the root of our environment, usually is the POSIX specification. And the problem with the POSIX specification is that it only allows for short options. It doesn't allow for long options. So long options are not in POSIX. Long options are actually part of the GNU convention. And this like Go syntax, I would imagine that it actually comes from Plan 9, because, like, if you have only short options, then obviously there is like 2 different ways you could extend this to long options. So with this in mind, there is conventions for how tools on Linux behave, how GNU tools behave. And in general, if you are building like, a serious command line application, you really should be following those conventions, because otherwise people would be angry at you. This is not the case for IronBeetle. Our context is different. And again, I kind of like want to emphasize this again and again and again and again. In software engineering, there are no universal rules, universal patterns, universal approaches. There are, like, everything is conditional. Every like piece of wisdom in programming is, if A holds, then B might make sense. It is always an implication. It's always like, if those conditions are true, then the conclusion holds. But if the conditions are not true, the conclusion might not hold, and condition there. So IronBeetle is a database. IronBeetle really is focused on being reliable, and it is not a command line tool. I mean, like, you run it on the command line, but you don't run it interactively, and usually at like some kind of like service environment does this for you. So the thing that invokes IronBeetle is usually a different program and is not a human. So we aren't really interested in, like, given like the most concise and conventional command line. We are interested in giving like the most unambiguous possible command line. So that's why if you go back to like this example, I think it's bigger still. Yeah. If you go to this example, you notice well, I mean, right now this is nothing unusual, but IronBeetle is unusual in what is not included. So first of all, we just do not support short options, which is actually, like, in direct violation of POSIX, because POSIX require you, mandate you to use short options. Yeah, like, you might support long options as an extension, but short options you must support. But we don't care about being compatible with POSIX specification, and we care about being super clear for the operator. So that's why only long options. This is, by the way, another like great conceptual thing. So if a tool supports long option and a short option, which one should you use? When you type on the command line, like, in your shell, use the short options, because there you prioritize conciseness, and you want to type faster. If you are writing a program and you are specifying options in some kind of like configuration file or a script or whatever, then please stick to long options. Because if you write a program, then the text of this program will be read by other humans, and they will really appreciate if you will spell out the options fully so that they don't have to guess the meaning. Again, because TimeBeetle is not intended for interactive usage and only for, like, real production usage, we only stick with long options. Then you see that we use like this equal signs before the option and the value. And again, usually people prefer to use just the space. And we thought about this hard, and our decision was that, hey, we actually don't want to support this syntax. If the option takes a value, we mandate that there is an equal sign. And the reason for that is that, again, it kind of like removes ambiguity. From the perspective of the program, of course, there is no ambiguity. Like, a program knows if a flag requires argument or not. So it is clear whether the 0 here is a value for the replica option or a positional argument. But you, as a user, you actually don't have this context. You need to know the specific command line tool options to realize that, hey, this is actually a value. So that's why we kind of like make it unambiguous on the command line that, hey, please use equal sign. So this logic is documented in our like CLI guidelines. So yeah, like in purposes robustness. So we kind of like use key value syntax and all the stuff. Again, you might want to consult this. This is in a file called flags.zig. Again, this is not something you should use for your next program. Whenever you design command line argument syntax for your next program, like, please take into account the context of that program. But this is what we use for TimeBeetle. Now, the way this actually is implemented is, let me show maybe some examples. With the help of media programming. So we have these minor fuzzers binary, which allows you to run a particular fuzzer, and you could specify like the size of the fuzzer. Like, do you want the fuzzer to finish quickly, or do you want to run it like for hours? And you could specify like a random seed. And the way we parse these command line arguments is that we just pass this type to this function and get back CLI arguments. So there is no manual parsing. We use infrastructure there. I think this is like really important. I think it is really important that you do not parse command line arguments by hand unless you have, again, a very specific context where that is required. Why is it? I think one of the biggest values when you develop software is flexibility and speed, ability to iterate quickly. Like, if you want to quickly throw together some kind of like a command line tool to run some experiments or whatnot, it should really be trivial to do that. If you want to add an extra parameter to your program, you should just like be able to go and do this. And that's why it is important to remove friction from those kinds of workloads. And like, you know, if adding a command line argument requires like writing a bunch of parsing code, then this is going to be friction. And the problem with friction is not that, like, you know, just takes time. The problem with friction is that it will actually distract you from the main goal. It will actually increase the activation energy to go and run that experiment. So the second order effects are quite high there. And this is actually one of like the first thing I did when I joined IronBeetle. I realized, hey, like I'm joining this project, I'm really going to write a boatload of different tools here, and I'm not going to parse arguments manually, so I need this command line parsing library. And therefore, the Flux library was born. Also, this is kind of like half of the story. The second half of the story is that as a Rust programmer, I really want to learn Zeek's meta-programming abilities, and parsing command line arguments is like really, really freaking cool use case to explain why comp time is so expressive. Because I also have like a similar, so this Flux library, which we'll be looking at today. Like I wrote it, and I don't claim it's like a particularly good like command line library. It's good for technical use case. But it's interesting that I had like essentially the same problem for Rust Analyzer, and there, let me quickly check that. And for Rust Analyzer, I wrote this tiny X flags macro, and like, you know, flags, X flags, like, you know, I'm bad at naming things. And the difference between the two is instructive, because fundamentally this is a meta programming problem. Like, you know, you want to statically describe a type and automatically have a parser generated for it, so you need to like somehow like generate the code. And in Rust, of course, this has to be solved with macros. And one of the learnings from this exercise is that macros do not have to be super slow. So if you want to, so even procedural macros, I think this is procedural macro. Let me see dependencies. Yeah, so it has a proc macro is I don't even remember whether it's like, you know, procedural or macro. For example, this is procedural macro. So procedural macros in Rust has a reputation of being slow, and it is kind of like partially deserved. Like, you know, no matter how you slice it, they're going to be slow. But the biggest part of slowness in procedural macros comes not from just that being a macro in a separate process, but rather from the need to parse Rust code. Because usually the procedural macros in Rust work by reflecting on the source code of your program. And the source code is naturally written in Rust, and Rust is a complicated language with complicated syntax, and it requires just like a lot of code to like parse this. So if your procedural macro has to parse Rust, then it has to be slow. That's why for Xflags, my design decision was to not parse Rust code, to base the syntax on a DSL, which actually generates Rust code, because generating Rust code is much easier than parsing it. But anyway, it's kind of like, macros and macros. I don't love this script. Like that was the best way I could solve my problem, but it's kind of like still, yeah, macros. It's interesting that in Zeek you don't have to jump through those hoops at all. You just say, okay, this is like CLI flags, and we pass it to our flags parsing function, and we do get CLI args back. So it's like nothing fancy here. Like the only fancy thing here is with this like double dash thing, which is how I signify positional arguments, which is kind of like just like, a silly bit of like DSL, but well, why not? Again, this is probably not something I would do for like wobbly published library because it just like, looks weird. But for us, I mean, it's fine. So I guess we could look at like a real CLI definition for the actual TagBeetle command. So you see it is union enum, so it has a bunch of subcommands. And then, like, for example, the start subcommand itself has like a bunch of arguments. So yeah, that's how it works. Okay, so let's see how you would actually implement this as a sort of like Zeek person tutorial. So we have this parse function which takes a runtime parameter, the iterator over our command line arguments, and it takes compile time parameter, the type we want to return. And we return. So okay, what do we do next? We call parse flags. Again, this is a place where we're going to do some substantial amount of comp time logic. So we say, hey, Zeek, please increase the amount of computation you are willing to extend us. And that's actually, okay, this is, yeah, like Twitch doesn't, so we have reports that Twitch does not work. So, okay, I think I should just go and maybe pin Europe version to Twitch until they fix it. Right. Okay, so yeah, there's like this ideas that, hey, we have like Turing-complete languages, and Turing-complete languages allow you to write a program which may loop, allow you to write non-total program. So let's maybe like design a language where everything is guaranteed to terminate. And this is kind of like, it feels like it's what you should do. Like, if you use like a real language, then it might not terminate. So let's like try by design to make sure that it terminates. But it's actually not what you want in practice, because in practical terms, a program which never terminates and a program which takes 1 million years to terminate are equivalent. And there is also, like, very fancy theoretical connections between the two. Because yes, you could take something which is primitively recursive, and that means you cannot implement a Turing machine in that language. But what you could do is that you could say, okay, let's try to run this Turing machine for like 100 million iterations. And if it stops, then that's the answer. Otherwise, we say, hey, I don't know. and that you can implement in your non-Turing complete language. And that essentially gives you, like, the same expressive power practically, because like no one needs programs who run for slightly less than eternity. So that's why this kind of like set eval branch quota, you shouldn't look at it as some kind of like, hey, it's like a dirty hack simply because Z cannot guarantee that like its time terminates. No. You will have exactly the same thing in every production system because everything that is expressive enough to express meaningful computation will have the ability to express this. Hey, let's try running Turing machine for 1 million steps, and you want to protect against that. So, okay. I think parse flag, if I remember correctly, it is going to be a recursive function. Allowing you to parse subcommands. And subcommands might or might not have the arguments overrun. So you could express so there is the foo command, which has an extra flag. And then there is a bar command, which doesn't have an extra flag. So we will invoke parse flags recursively for this case, which is a shorthand for void. So that's why here we say, okay, if our flags is actually like void type, then we don't expect any arguments. And that's why in the top level, we actually assert that, hey, the type itself is not void, because if you parse arguments, like you better actually have some arguments to parse. So, and this is, by the way, this is, okay, sorry. So, folks, I'm kind of like promised you like a silly, simple thing about like command line programs, but I'm going to digress into like interesting like general observations like primitive recursive functions and Turing complexity and whatnot. So another observation is that if I were writing this in the beginning of my career, I would probably do this. I would probably say, hey, I mean, like this is a recursive function. So, and it kind of like sounds like just what I want to expose it. So like let's make this public interface. And today, actually, I try to avoid this. I try to ensure that there is a very strict separation between public interface and the implementation. So parse is public interface. Parse flags is an implementation. And this allows me to actually, like this mechanical separation, like even if I start with just this, allows me to notice that there is some differences and that I could actually go and weaponize it. So for example, again, parse flag is recursive, so it has to deal with void arguments. But actually, I know that my top level parse is not recursive, and then I can assert that the argument is not void. I could also like have this like extra convenience for skipping the arguments and that sort of stuff. So like for recursive functions, this applies doubly, but in general, like, if the function is called in the implementation, don't expose it directly, even if the public interface is essentially the same. Like, do like help your future self and do have this separation between public and private. So, question in chat. It's interesting that Zig looks a bit like TypeScript with colon type and the return type at the function declaration. I mean, all modern languages look the same. I think name type value actually went from ML, a family of languages. And the reason for that is that this makes it easy to avoid the type, like from the parsing from the LL parser perspective. And I mean, it's just nice syntax overall, so it's not really surprising that like all modern languages like Rust, Swift, Kotlin, TypeScript, they essentially look the same. So, okay, let's go back to our parsing. Now, if our type here is a union and type info is, so, okay, how would I describe it? Okay, so flux is like a type, but actually there isn't like many things you want to like, you know, you could do with type. You could essentially in Zig just like, you know, compare type to the quality. And we want to like know like what kind of type it is. Is it a union? Is it a struct? Is it like built-in type, something else? And for that, Zig has type info function, which gives you like a struct which describes the type. So let's see. The return of type info is essentially this thing. So this is like the exhaustive list of all the types that, all kinds of types that Zig has. So we have like, you know, bool for bool, int for int, union, and then if we go inside, well, union is hard, let's see struct, yeah. And if we go inside the struct, we'll see that, hey, it has like fields. And the field has a name and a type. And again, a type is a type with like lowercase letter. Okay, I'm glad that Europe works for you. Okay, type with a lowercase is like an actual type. And to get from this type to like this type of a capital T, you again need to recursively type info on it. Actually, I'm not entirely sure why it works this way. Perhaps we could say that, hey, type and its type info are literally, well, okay, yeah. I know why we do not want to make type and type info literally the same. Because, like, you know, okay, so if I type, oh, this is such a perfect example. Because if I type flux default value, what I actually want to see is default value function implemented on my type. I don't want to see, like, you know, this kind of like default function implemented on the type of type. So that's why the separation. So anyway, we basically check that we are a union. And if we are a union, we go and we parse a subcommand. So if we are parsing a subcommand, we obviously need name of the command. Otherwise, we have, oh, another bit of high level stuff. So error handling. Error handling is, I think, one of the unsolved problems of language design. Like, it's super hard to invent a generic way to handle errors which works for all circumstances. But as usual, it's rare that you need to do something which works in all circumstances. Like, you know, if you are a language designer, like, you know, it's a tough job. But if you are working with a specific problem, you have very specific requirements, and your requirements might not be general. So for the purpose of parsing command line arguments, we know that what we are going to do if there is an error is that we are just going to terminate the process. There isn't really much we can do. So that's why a design decision here is that we don't actually bubble any kind of error here. We immediately and safely crush, preaching the error. So that's why if we are parsing a subcommand and there isn't any argument, we fail with an error message, which means that we print to standard error and then exit with code 1. That's it. Okay, then we automatically implement help. And again, okay, let's see these. So in our top level command line, you see that we actually have this help message. And like this is like manually written help. So usually when you do command line parsing library, it can generate help for you. And the problem here is that generating good help is actually like pretty hard because you need to solve line robin. So it might actually be easier to, like, if you are going for like, great help message, it's easier to just go and handcraft it exactly as what the user will see. Because we only have one public command, which is IronBeetle, and everything else is just like internal tooling where you could check the source code, we figured out that we actually don't need poorly implemented auto-generated help, and we do want like, really high quality help. So that's why we're just going to write it manually. So the way this is implemented is that we check at compile time that if the command has this help declaration, which is public, and the user parsed -h or -help, which is incidentally, I think, the single case where we support short argument, we'll just again go and write out the help command, and then we'll go and exit successfully. Again, don't try to overthink it. Like, you know that after the help you're going to exit, and yes, maybe for full flexibility you want to allow the core to customize what helps, what happens if the help argument is specified. But I mean, we don't write this as a reusable library for everyone. We write it for only for typing, and we know that just exiting is like the simplest possible thing that could work. If you are new to comp time programming in Zeek, like it might be like super like confusing that I'm saying that this happens in command line. So like let me be clear here. So this line is executed compile time, but this obviously has to be executed at runtime because the first arc is runtime parameter. And you see, like this is kind of like the beauty of Zeek, or the ugliness, depending on your point of view, like how you could just seamlessly weave together comp time code and runtime code. And like there are like two questions here. One is like how you figure out what's running at comp time, what's running at runtime, and the second, like, what if you make a mistake? Like, will this end terribly? So let's start with the first question. Like, how can you figure out if something is running at comp time or at runtime? Well, the simplest possible thing to do is to make this explicit. If you want to explicitly mark code as running at comp time, you prefix it with comp time keyword. And that requires that either code is fully executed at comp time or you get a clear error. Otherwise, the rules in Zeek is that Zeek tries to execute everything as much as possible at comp time. So comp time is really default. Runtime is a fallback until the function call boundary. So if you see a function call, then the function call is always going to be runtime unless it itself exists in explicitly comp time scope. Looking at this code, I see that, hey, this is built in, so I know that this built-in is going to be executed at comp time, and then this entire if is going to be executed at comp time. So the runtime code, which will get generated for a particular command, is going to be either this or this. And the way, like, you see that here we kind of like checked if commands has this field, but here we could just like directly affect it, because that's again like the beauty of Zeek's time semantics, because if this value is to false, we won't actually look here. Like Zeek won't try to touch it here, and I mean it could be like some complete garbage there, and it won't prevent a compilation because Zeek is lazy. Okay, so we dealt with helped. Otherwise, well, we need to check if our subcommand matches our flag. Again, mixture of comp time code and runtime code. And you see, so standard meta fields is a helper function which takes a type and returns its fields. So for union, and command is a union. So for union, it's like all like the union members. This is a function call. So by default, it is going to be executed at runtime. And if I remove this comp time, the Zeek will complain that, hey, this is a function call, so I try to execute at runtime, but actually I cannot execute this at runtime because this thing only exists at compile time, so I'm like failing. So that's why I kind of say, no, I really do mean comp time here. And then this is inline. So for like if command is something like this, what we'll essentially have is like one copy with who, and then one copy with bar. So that's what inline does. So essentially, inline specializes the for loop on the length of the stuff you pass in, and that's actually like this is pretty neat. So you could inline for over an array with comp time known length and runtime known elements. But in this case, both the length and the elements themselves are known at compile time. So okay, we assert that field doesn't contain underscores, just to play it safe, and whenever we'll need underscored command to explicitly make the decision. And if our argument matches the field name, then we recursively invoke ourselves with the type of that field, and we return the actual specific union. And that's kind of like okay. So yeah, I guess I need to explain it. So let's say let's go. Okay, it's not struct. Let's go back to our union enum example. So if you construct this thing normally, you would say const cli equals who right? And here we essentially want to say something like return. And here we kind of say field name equals parse flags, right? But there isn't actually Zeek doesn't have quasi-quotient syntax so you can't really like do this. But there is this union init function which a built-in, not function built-in, which does essentially this this syntax. So we kind of like say, let's write dot curly brace and let's initialize like this field. And again, this all is happening at compile time. So if this doesn't type check, if the union doesn't have this field or whatnot, you will get a compile time error. You don't get like some wild undefined behavior. Okay, and if there isn't a mentioned subcommand, then we fail with an on command. So let's actually start this. Let's see, can we eat my data? Well, unknown subcommand eat my data. Yeah, this is exactly how this code works. Okay, let's go back to parse flag. So right now we like deal with this like recursive union type, and we deal with like trivial void type. So now we have void a reminder. This is like for subcommands without any further arguments. So now let's get back to actual struct case. Okay, we again look at the fields of our flags, and actually, I'm not. That's interesting. So I don't get why. I'm not required to write comp time here because yeah, it feels like actually like, can this be comp time? Can this be runtime field? I don't know. Well, is it marked inline? It's not marked inline. Okay, so this is something I don't really understand because, how does it work? So okay. I'm officially stumped here because like the rule I know that hey, function calls are runtime thing. So I would expect this to be like runtime thing, but apparently Zig somehow decides that hey, because those things are comp time only, this thing is actually comp time only somehow. Well, anyway. I guess this kind of like goes back to the question is that, yes, you might be like confused what things are runtime and what things are comp time, but it never really like leads to errors in practice, because if like something cannot be comp time or something cannot be runtime, you get an error at compile time. And the only case is that so something which could be comp time but turns out to be runtime, but that is actually fine, and that at most costs you performance because the behavior is guaranteed to be the same. Okay, so I think here we are dealing with that syntax I was showing you. So everything before double dash are named arguments, everything after double dash are positional arguments. I'm not sure what fields, well, fields extended, I think it's kind of like the place where we slice those into. So we go for fields, and if we reached our double dash, we say, okay, Everything before is positional fields, everything after is everything before name fields, everything after positional, and this like the breaking point. Otherwise, everything is name field. Okay, then this is kind of like another pattern. Like you could just make the whole block comp time, and then it's like doubly sure that hey, nothing runtime can happen here. Here, I think we are going to sort fields, so that yeah, like if one argument is a prefix of another, then we should try to match the lone argument first. So we sort the arguments, and then further we want to do various sanity checks on the values of arguments. So if our argument is a Boolean, we require that it always defaults to false. Again, like another principle, like if you don't have public users, if you don't have to care about code being reusable in every context, it makes sense to always go for the most restrictive variant first, because relaxing is much easier than tightening. So we require that Booleans always have an explicit default equal to false. We similarly require that optionals have always explicit default to null, and that the value is valid. And otherwise, we assert that valid value type. So what is value type? So we support strings as arguments, we support int, we support custom parsing through parse flag value function. We support exhaustive enums, and enums, so what Rust calls an enum, Zik calls a union. And what Rust calls a fieldless enum, I think the official terminology, is what Zik calls an enum. Okay, that's it. And then for positional arguments, we require that it always first required and then optional. So we go through all positional arguments, and if it doesn't have, if it does have a default value, that means that it is optional, and we signify that hey, we are in the optional tail of the arguments. And if we find an argument while we are in optional tail which doesn't have an optional value, we say hey, optional position argument might be threatened. This is a panic, but this is panic inside comp time. So again, this is essentially compile error. And then, yeah, similarly, we check that optional flags have a default and they have valid value types. Okay, so we massaged our arguments, and now we actually do the parsing itself. Some arguments are optional. Some arguments, so they might be present 0 or 1 time. Some arguments are mandatory, so they must be present exactly 1 time. The way to code this most straightforward way is just to count how many times we saw each argument. And this is what our line does. So let's see, past tests, do we... yeah, so we have like 1 optional argument, 2 optional arguments, and 1 required argument. Essentially, what we want to get is from this argument. Okay, question, what's IronBeetle? So Short version. IronBeetle is a weekly Twitch, YouTube, and X stream where we read the source code of TagBeetle, this database for financial accounting, and try to understand how the whole thing works. Okay, and in this episode in particular, we are looking at how TagBeetle parses command line arguments, like super simple, stupid thingy, but well, you gotta parse command line arguments. So we want, like, when we parse these, we want to make sure that we get exactly one fuzzer and at most one event max and sit. Essentially, we want to have this struct. So just like, just count all the things. And this magic spell here does exactly that. So let's see this with example. So flags is like this thing. Then field enum will transform this into this thing. And then enum field struct takes this kind of enum and slaps, so it turns it back into struct and slaps e32 as a type, and 0 I think is default. So that's kind of like neat. And again, this isn't some kind of like macro. This is just normal Zig code. Actually, we really do need to read implementation of those functions. I just realized, like, well, we should totally cover Zig standard library. Okay, maybe we'll actually do this next time, because I kind of like want to slowly start wrapping up this episode, because as usual I kind of like wanted to, it happens like every dumb time. I wanted to cover flags and snapshot testing today, and looks like we covered like half of the flags. But well, that's why we have more than 100 episodes at this point. Okay. So let's... do we want to plow through everything here quickly, or would we rather take it slowly? Yeah, actually, I realized that there is a bunch of more stuff that I want to cover here. So let's kind of like leave these for the next episode, where I try to cut the amount of like meta I'm talking about, and like stick closer to, like, object level, which is for us actually meta programming. And then we'll go through in detail for like everything else. Okay, so let's maybe then wrap it up for today. So we started looking at TagBeetle's command line parser. The lessons here. So the first lesson is command line parsing is unfortunately ill-defined problem. There isn't one specification of what a proper command line is, which everyone agrees to. Everyone is doing their own thing. So first and foremost, please take, so that's kind of the first lesson. The second lesson is that there are no universal answers. Context is everything. In the context of TagBeetle, we are not aiming to be a blend-in command line application to be used interactively in your shell. We are a systems programming project, so TagBeetle will be invoked by other programs, not by humans directly. So we design our command line syntax to be maximally simple and unambiguous. The second lesson is that you should be using a library for parsing command line arguments. Not because, like, you never should write code yourself and you always use dependency. No. Like, by using library for parsing arguments, I mean, like, you write your own library like we do here. But the reason is that you want to remove the friction of adding and removing command line arguments, because that is how you run many experiments. And experiments are what enables quick velocity. So so parsing command line arguments is a common source of friction. That's what I'm trying to say, and you want to eliminate it. Finally, what we kind of started looking at is that parsing command line arguments is a great showcase for this CompTime feature, how you could seamlessly blend in compile time code and runtime code to solve what Rust solves with macros, but with significantly less language machinery and arguably with significantly more understandable resulting code. So if you want to learn more about this, then please join us on Twitch, X, and YouTube next week at 5 p.m. UTC, live on Thursday. And see you then, and goodbye.